But yeah, thank you so much, everyone, for joining today. My name's John from the Institute for Quantum Computing. We're a research institute at the University of Waterloo. Thank you so much to Svetlana, to Samantha, and everyone who helped organize this, as well as the whole series of talks. It's been really great to see these kind of ideas able to be more accessible in this way. So there we go, clicking. There we go. So a bit about myself, my background. I am a quantum physicist. I got my PhD in quantum physics from the University of Waterloo in 2016. I got into quantum in the same way a lot of people get into quantum, by having a really good experience in grade 12 physics when we finally get into that little quantum unit that's kind of tacked in there. We spend a lot of time in physics talking about forces, talking about motion, talking about waves, those kind of things. And then at the very end, they tell you, and actually, there's a whole bunch of other stuff out there too. And it kind of opens up the world in a big way. So when we start learning about some of these ideas, it really does kind of spark the imagination. And I ended up using that as a reason to go into physics. Got my PhD looking at how we explore some of these systems, essentially using really, really, really powerful lasers to look at incredibly small amounts of light and see how we can learn things about quantum mechanics by studying that light. Since 2018, I've been working in quantum outreach, how we talk about quantum mechanics, how we can educate people about quantum mechanics, how we can build hands-on experiments to help people learn about some of these features of quantum mechanics. That's what I spend my days doing, spend my nights hanging out with this big furry monster down here. Okay, so what is quantum? So if you've attended any other talks in the series, you probably don't need it defined, but just in case this is your first one. So what is quantum? Well, quantum is really the rule book of that submicroscopic universe. So it describes the behavior of things like atoms, photons, and electrons, things that exist below what the eye can see. Now, it does introduce some new ways to think about the world, which is why it's sometimes viewed as unintuitive. We have things like quantization, this idea that things can only exist in discrete units. Certain properties are discretized in that way. We also have things like probability waves that have no classical analog. These don't always match the way we usually think about the world around us. But importantly, if we understand these rules, even if we don't have a picture in our mind about exactly what it might look like, it's very difficult, if not impossible, to do that. If we use these rules and apply these rules and start to build intuition about these rules, things like the uncertainty principle, things like Schrodinger's equation, we can use that to predict the behavior of these objects very accurately. We've been using quantum mechanics for about 100 years at this point. A lot of people in the early days thought we would find some other kind of theory that exists beyond quantum mechanics, or that we would find holes in the theory of quantum mechanics, but it's withstood every test we've managed to throw at it experimentally and proven to be one of the most predictive models of physics humankind has developed. It's also been used to develop a lot of technologies we use today. So even if we don't walk around thinking about quantum mechanics all day, every day, or at least not most of us, some of us do, understanding quantum mechanics has built a lot of technologies that we do use every single day. Things like lasers, for example. Laser stands for light amplification by stimulated emission of radiation. That process in there, stimulated emission, is understood through the lens of quantum mechanics. Things like nuclear power are understood through quantum mechanics. Magnetic resonance imaging essentially works because your body is made up of atoms. Each of those atoms has a nucleus, and that nucleus has a tiny magnetic, essentially acts like a little tiny magnet through a quantum property called spin. And by manipulating that spin property, we're able to get these images of the inside of our body. Atomic clocks for GPS. If we want to have GPS work, essentially what we need to do is have our phone communicate to different satellites in space and have incredibly precise timing information on how long it takes a signal to get from our phone to those satellites. The only way we can have that timing precision is using clocks that work on atomic physics and quantum mechanics. And also things like electron microscopes, which we probably don't use in our day-to-day life. But if you haven't spent time going down an internet search rabbit hole looking at pictures of bugs under electron microscopes, I highly, highly, highly recommend doing it. Quantum technology is also having a bit of a moment right now. So we've used quantum mechanics for a long time, but there is something in the water, let's say right now. There's a lot of people talking more about quantum technologies in the past 10, 20 years. So we've seen in very recent times about $44 billion worldwide being invested in quantum technologies, including many billions in Canada through things like the National Quantum Strategy. Just earlier this year, the G7 leaders gathered in Kananaskis and agreed that quantum technologies was an important area of interest that the G7 would explore collaboratively. And also the United Nations, their scientific arm, UNESCO, named 2025 as the International Year of Quantum Science and Technology, celebrating 100 years of using this science to build real technologies and looking towards the future at new technologies that will be developed based on quantum mechanics. Okay. Now, one of the reasons why people sometimes talk about quantum technologies as if they're new is because there is a new thing out there, and it's called quantum information science. So this field is only about 30 years old, which is incredibly young on the scale of scientific fields. And what we do here is think about how we encode information in systems and what might change if those systems obey the rules of quantum mechanics. So instead of encoding information in something classical, we're going to encode it in something that obeys the rules of quantum physics. Now, this is how we think about building things like quantum computers, which can solve some problems much more efficiently than today's computers. This is how we think about quantum communication networks that have enhanced cryptographic security. Think about quantum sensors that take information from around the world and give it to us in a form that we can understand. Think about building new kinds of materials where the quantum interactions between the atoms inside that material are important. And also think about quantum foundations, just really understanding what quantum mechanics is telling us through the lens of information theory. And when we start talking about quantum information science, it's important to note that this field is much, much, much bigger than physics. There are people working in it in computer science, mathematics, cryptography, chemistry, physics, engineering, philosophy, biology, medicine. All these different fields start getting folded in when we start considering how we might apply quantum sensors, or how we might build quantum computing algorithms, or how we might ensure that a quantum network is indeed cryptographically secure, or when we start thinking about what it all means in the first place, or start trying to take any of these products to market, for example. So when we talk about quantum physics, if you're interested in this kind of field, but don't get me wrong, I'm a physicist. I'm going to encourage people to study physics. But if you're going down a different path, but you're still interested in this quantum stuff, there's a lot of different ways to get involved. Now, we're talking about quantum computers, so it's probably best if we take one quick second and back up and ask ourselves, what's a computer? Because we use them every day, and at one point they were a completely novel invention, but now we use them every day. We kind of take them for granted. So let's take a step back and think about what a computer actually does for us. So generally, we're going to use our computer to play video games, browse the internet, do mathematics, those kind of things. But at the end of the day, what we're doing is giving it problems. So I have my computer in front of me here. I might type something into it that says, tell me what 3 times 5 is. And then something's going to happen in the circuit board. I'm going to get the answer out that says 3 times 5 equals 15. I might say, make a connection over Zoom so I can make this presentation. And it's going to do something. And all of a sudden, I can see you on my monitor and you can see me through the magic of the internet. I might ask it, show me a picture of a dog. It's going to do some search, bring me back a JPEG of a dog, for example. In all of these situations, what we can boil this down to is I'm giving my computer some information, some input that I can generally express as a string of zeros and ones. So I say 3 times 5, that's going to get converted into a whole bunch of zeros and ones through a layer of hardware and software so that the computer can understand my question. The computer is, for all intents and purposes, for our purposes anyways, a black box that's going to take those zeros and ones, shake them up, move them around, do some calculation with them, and then give me some output corresponding to the information I need. I already knew the numbers 3 and 5. It's going to tell me that 3 times 5 equals 15. That's my output. I already knew that word dog. It's going to give me a JPEG represented as a string of zeros and ones that corresponds to an image of a dog. I give it a problem. It gives me a solution. So if you've ever opened a computer, though, you might see that it's full of circuits, motherboards, chips, all those kind of things. And these circuits, think about how we're encoding information there. Essentially, they're obeying the laws, things like Kirchhoff's laws, Ohm's laws, the rules of electricity and magnetism. But what about if we were to encode those zeros and ones in something that obeys the rules of quantum physics instead? Something where quantization, interference, probability waves, where those ideas become important. Okay? So what's a bit? How could we think about encoding a bit into another kind of system? Well, if we want to encode 1 bit of information, we need something that can represent 0, something that can represent 1. So we need what we call mutually exclusive states. They need to be distinguishable. We can tell them apart. And exclusive. It can't be both at the same time. Now, mathematically, we're going to represent this as a 0 and a 1. That's kind of the theoretical model we're going to use. But at the end of the day, the 0 and 1 is a mathematical model. Just like any mathematical model that we use in physics, it has to be implemented by something that really exists, something we can hold with our hands. And that could be a light switch being up or down. That's a bit of information. It could be a light bulb being on or off, 0 or 1, a coin being heads or tails. And yes, to go back to a classic example from quantum science, a classical bit could be encoded in if a cat is alive or dead. This is not an ethical way to encode a bit, but it fits the definition. Now, modern computers, they'll use voltage and circuits, but this is not the only option. Okay, so let's consider these two options here. We have two ways we can encode a bit. We have a simple circuit with a battery and a switch and a voltmeter. And if we measure the voltage across that circuit, if the switch is closed, then there will be the voltage of the battery. If the switch is open, it's an open circuit. There's 0 volts in the circuit. And we have this other option here where we have an atom drawn in the simple Bohr model. We have a positively charged nucleus and an electron that can exist in discrete orbitals. And if it's in the ground state or the excited state, that could be one bit of information as well. If it's in the ground state, low energy, call that 0. And the excited state, high energy, call that 1. Now, if we go back to the circuit, that's relatively similar to how we build computers today. And this follows the rules of electromagnetism, Maxwell's equations, Kirchhoff's laws, Ohm's law, current, voltage, resistance, those kind of ideas. Whereas if I think about the atom, well, that bit could be in the low energy or the high energy. Those are our bit states. But how do I describe the atom? What rules of physics do I need to understand how the atom works? Well, those quantized orbitals, those quantized energies, are described by the rules of quantum mechanics. So this is an example of what we call a quantum bit or a qubit. It is a bit of information encoded inside one single atom. And if we want to understand how to manipulate that information, we need to understand the rules of quantum mechanics. Okay? And that might have been a bit of a heady idea. Let's kind of break that down a little bit more. Okay? So let's look at this log, for example. We got a log, good old-fashioned piece of wood. It's made of atoms, right? We know that everything around us is made of building blocks, atoms that form molecules and crystals and all that sort of stuff. And on the big scale can form things like this log we're looking at right now. So it's made of atoms. Those atoms follow the rules of quantum mechanics. Is this log a quantum computer? Well, that's not quite enough. Let's think about a grain of sand, something quite a bit smaller. Turns out there's something like 10 to the power 20 atoms inside that. And that's also not a quantum computer. It's not enough for these qubits to be existing. It's not enough for these atoms just to be there. We need to isolate them and we need to be able to control them. So what we should really asking ourselves is what is a useful way to encode a bit of information into something that obeys the rules of quantum mechanics? So generally speaking, it's not enough to just be quantum mechanical. We need to be able to harness the uniquely quantum behavior. So we should be able to grow the system to many individual atoms. We need those atoms to be isolated and stable. We need to maintain something called quantum superposition states. We need to be able to control those atoms, flip them from the 0 state to the 1 state and back again. We need to be able to individually measure each atom, and we need to connect different atoms together to solve larger and larger problems. So it's not enough that we just have atoms. We need to be able, or have photons, or have something that obeys the rules of quantum mechanics. This is what makes it different than something like a laser or like an MRI. We're not interested in controlling all of them together. We're interested in controlling individual quantum systems, individual atoms, individual photons, for example, individual electrons. Okay. And now, thankfully, there's a lot of ways we can do that and a lot of ways that people are pursuing it. We can think about individual atoms and ions controlling individual atoms, individual units of matter. We can think about controlling individual units of light, photons, for example. We can use that spin property that they use in MRI technologies for quantum computing as well. And also we can use things like superconducting circuits where we cool things down to incredibly cool temperatures and use the current in those circuits instead. These are all ways that people are approaching building quantum technologies like sensors, communication systems, and computers. And no one really knows which one will be, let's say, the most important to build quantum computers of the future. So at the bottom here, we have a lot of companies, including some major companies like IBM, Google, Microsoft, Intel, as well as some Canadian companies like Xanadu, Photonic, D-Wave, Anion, for example. And all of them are working on these different systems, some for quantum computing, some for a more broad set of technologies. But it's important that we're investing in all of these. A, because we don't know which one's going to scale up to build a useful quantum computer first. B, because we don't know if certain versions of these quantum computers will have advantages for different problems. So it might be worthwhile to build an atom-based one and a photon-based one to solve different kinds of problems. Okay, so let's dive into a few of these qubits. We'll do some demos and we'll talk a bit about how we actually isolate these systems and use them to encode quantum information. And to start, we're going to talk about photonic qubits. So a photon is the smallest possible unit of light. If I go down to that quantum level, I can either have 0 photons, 1 photon, 2 photons, 3 photons, but never half a photon or pi photons. They kind of exist like this little bit of a ladder. There's always 1, 2, 3, 4, these integer unit steps. Now, how can I take a single photon and encode information to it? So first off, how do I create a photon? I actually do that using something like this. So this system we're looking at right here is something in one of our labs that's called a Sagnac interferometer. Inside this piece where the blue laser hits is a little tiny piece of crystal, and sometimes that blue laser will split into 2 red photons, and those red photons must come out in pairs. If I measure one, I know there's another there, and that's how I can generate literally one photon at a time. Now, how can I encode information in that single photon? Well, one example of how I can do it is using the polarization of that photon. So for example, what we can think about is the wave nature of light. It carries an electromagnetic field, and that electromagnetic field must be oriented in a direction perpendicular to the direction the light is traveling. So if light is traveling towards the camera, the wave can be side to side or it can be up and down. So we have these little polarizing slides here. You can see on my camera that they have an arrow on them. So I'm going to put this one right on top of the camera. If I hold it this way, it lets through the vertically polarized light, but will absorb the horizontally polarized light. So right now, the way you're seeing me on the camera, we are only seeing the vertically polarized light going between my face and the camera. Now I have another vertical polarizer here, but we'll see that if I rotate this to horizontal instead, it actually blocks out all the light. You can see a bit of reflection from the screen there, but I go away. It becomes opaque effectively. So aligned the same way, aligned opposite ways. Now we can use this to create a communication system pretty easily. So right now we're only letting through vertical light. If I hold my polarizer this way, I'm effectively sending a 0 to you. If I hold my polarizer this way, I'm effectively sending a 1. And we can tell based on whether the light gets through or not. So polarization of light, that's an example of how we can build mutually exclusive states into light and indeed into individual photons and use that for quantum computing and quantum communication. Okay. Now we also know that light does behave like a wave. Some of you may have seen water wave experiments where you drop 2 rocks in a pond, the 2 waves then propagate outwards, and then when they meet, if they're going the same way, they make an even bigger wave. And if they meet and they're what we call out of phase, they're opposite to each other, they're going to cancel each other out. We can see that with light as well. If we shine a laser through 2 slits, we call them 2 very, very narrow gaps, the light will expand through one and expand through the other. And sometimes when the light waves meet, they'll make an even bigger wave. Sometimes when they meet, they'll cancel each other out. We'll end up with a pattern of what we call constructive and destructive interference, like we see right here. Okay, so sometimes where we see even brighter light, and sometimes where it actually completely blacks out. That's what we call destructive interference. Okay, and if we model light as a wave, we can predict this perfectly. So we seem to have these 2 somewhat conflicting models of light. Light is an electromagnetic wave. We can see that through wave interference. But we also know that light is made up of these indivisible units that we call photons. So how can we square this circle? How can we try to see if we can see both features at once, perhaps? So thankfully, we know how to do this. So we already talked a little bit about how we can make photons one at a time. So let's make photons literally one at a time and try to repeat the double slit experiment. So we're going to start out with our photon machine here. It's going to spit out photons one at a time, and we're going to send them into the double slit experiment. And we're going to put our photon detectors, which are these little red semicircles here, right on the back of those slits. Okay? And what we see is sometimes the photon is in the left slit, sometimes it's in the right slit, sometimes in the right slit, sometimes in the left slit, goes back and forth and back and forth and back and forth. Well, not really back and forth. It's always randomly in one or the other. But we don't know which one it's going to be in. Very importantly, it's never in both at once. It's always in one or the other. Okay? So what happens if we move our camera very, very far away from the slit so that the light has a chance to spread out and we no longer know which slit it actually went through? Are we going to see the photons just distributed out, or are we going to see the interference pattern like we saw with a wave? Once again, we have the tools. We know how to build photons. We know how to detect photons using things like avalanche photodiodes. We have tools that can really detect individual photons of light. So let's just do the experiment. Okay, and now this is real data taken at the University of Waterloo. Each dot we're seeing on the screen corresponds to one single photon being detected. Okay, so each white dot is one photon. At the start, it really doesn't look like too much. But if we let it build and build and build and build, we see that there are some regions, like here, for example, that are much more likely to see photons. We'll let it build one more time. And some regions, like here, for example, that are much less likely to see photons. So each photon is detected at a random place. But we see that the probabilities interfered with each other. We see that we are more likely to see photons in some locations than others. So we interpret this through the rule of superposition generally. The photon went through a superposition of both slits. It didn't go through one or the other. It went through a superposition of both. Some component of it went to the left, some component of it went through the right. With a 50% chance it went to the left, with a 50% chance it went to the right. Now, when we think about wave interference, we usually mentally think about that as energies interfering with each other. In quantum mechanics, it's not just energies that can interfere or intensities that can interfere, it's possibilities that can interfere. So these two possibilities, these two probability amplitudes, to use the technical term, interfered with each other. But if we measure which slit the photon goes through, if we put the detectors right there, we'll see it goes through one or the other, destroying the superposition and seeing no interference whatsoever. Okay. So these are some of the kinds of experiments that we can work on with photons. We can think about how we can use these wave and particle-like properties of photons in different ways. And indeed, kind of thinking about things through that lens is what's behind a lot of things like quantum cryptography and quantum computing. So this, for example, is the quantum photonics lab we have here at IQC, where they build things like that entangled photon source. They also do things like build satellite links to communicate using individual photons one at a time from the ground to an orbiting satellite and using that for cryptographic research, as well as building new kinds of sensors that can detect things with very, very high sensitivity. Actually, the student pictured here, Alex, runs a quantum startup called Phantom Photonics as well. So she's a student and a startup founder. And that startup is looking at how we can use photonic sensors in order to measure things underwater very, very accurately. These are some of the things we can think about doing using these photonic systems. Now, aligning these experiments can be a bit intense. So this picture right here is a picture of an experiment out of China that claims something called a quantum advantage. So essentially using a quantum computer for something that a classical computer cannot do. And it was a very cool experiment. And if we look at what this optical setup looks like, suffice to say there's 10, I think it's 20 or so different photonic modes that we're using. We have, sorry, 50 photonic modes we're using. 144 single photon detectors, God knows how many mirrors, just a ton of material in there. And for anyone who might have spent some time in an optics lab before, you're basically talking about graduate students working around the clock to keep this system working. It is a very, very labor intensive system to build. Now, if we want to think about using these for more practical things, especially in quantum computing, we need to move towards integrated optics and engineering those kind of systems. So this image, for example, is from Toronto startup Xanadu using their integrated photonic system approach for building up these systems. Okay. Now, when we talk about these things, when we talk about wave-particle duality, when we talk about seeing interference with objects that seem to be discretized, seem to be quantized, seem to be individual in nature, this doesn't just apply to light. So for example, in this image over here, this is the same effective experiment, but instead of doing it with individual particles of light, we're doing it with individual electrons, charged particles that have mass, that have an electric field that, we really do usually think about as particles. We can also see that in experiments like this, which are actually done with even larger and larger molecules. There's a group by Marcus Arndt out of Vienna, who that's basically their whole thing is how can we see interference effects with bigger and bigger stuff. In this particular one from 99, they showed interference effects using buckyballs, carbon-60 molecules, and we can still see that effect. So if we can see these same effects with photons that we do with atoms, reasons to say that maybe we can start thinking about doing some of the same experiments. And maybe we can start thinking about building some of the same technologies using these kinds of systems. So atoms, molecules, electrons, photons, they're very different, and the tools we use to control them are very different, but they follow the same fundamental set of rules. So if we can think about building quantum tools like quantum computers and quantum sensors out of photons, we can think about building analogous tools out of atoms, molecules, electrons, and other more exotic systems as well. So next, we're going to move on to talk a bit about atomic qubits. So we already talked a bit about how we can encode information in an atom using the atomic energy levels, ground state and excited state. But how can we control them? And to get a view of that, we're going to quickly flip over to the demo bench so that we can learn a little bit about atomic spectra. So hopefully everyone sees the demo bench now. Otherwise, someone please yell at me. But what we have here is just a white LED light. Yeah, plain white LED. And we have here a diffraction grating. So this rainbow filter here is called a diffraction grating. Think about it like a prism. It's going to split the colors of light. So if I hold my white LED here and then put the diffraction grating in front of the camera, we see that we can actually see the colors that the white LED is made up of. So white light, we know, is made up of a rainbow of colors that goes from red to purple. And if I put the color filter in, sorry, the diffraction grating in front of the camera, we can see the white LED split into its red, yellow, green, blue, purple components. Now, one thing you might notice about the spectrum, we call this the spectrum, the spread of the colors of the LED. One thing you might notice is that it's pretty smooth and continuous. It goes from red to blue and hits everything in between along the way. There's no gaps, there's no sudden stops. It is really the complete rainbow effect. Now let's compare that with this right here. So this right here is a tube of hydrogen gas that we're going to apply a high voltage to. And when we do that, we apply a high voltage to the hydrogen gas, we see we get this nice pink glow right there. Okay? Now let's take a look at that pink glow once again through the diffraction grating. And what we see is that that pink glow is not made up of just pink. And it's also not a smooth distribution. We see on the sides, we see that there is a strong red line, but also some blue, some cyan in there. This is what we call the emission spectrum of hydrogen. And if we measure those lines very specifically, figure out exactly which wavelength each color corresponds to, we can use that to identify hydrogen, which is used oftentimes in chemical analysis, solar observations, things like that. Now, each element does have a different spectrum. So for example, I'll turn on this lamp instead. This lamp is helium gas instead. It has kind of a beige yellow glow if we look at it with the naked eye. But once again, if we look at it through the diffraction grating, we see that that's actually made up of yellow, red, blue, and once again, a little bit of cyan. And if we look at these colors very specifically, we find that they correspond to helium. Only helium has these exact lines in this exact pattern. Excuse me while I quickly run back and switch my screen share back to the slides. Hopefully that showed up okay for everyone. And hopefully we're back on the slides now. All right, there we go. Okay, so each of these different kinds of gases, if we heat them up, we'll see different colors. So you might be familiar with neon light, for example, that has a very characteristic orange glow that is used in a lot of signage. And if we measure that exact orange glow, we see that it has these distinct spectral lines. We already saw helium live. Yes, it's used in balloons, but we can also measure those lines directly to identify helium. Things like mercury vapor, for example. Mercury is a liquid metal. If we heat it up so it becomes a vapor, then we'll see that it has a nice characteristic blue glow. So all these different elements have different glows, and we can measure the precise colors at which they glow to understand exactly which element we're dealing with. Okay, so let's go down the rabbit hole a little bit here. So each line we see, what it corresponds to is, remember how we talked about the atom, it can have these quantized energy levels, ground state, excited state, another excited state, and so on. This is the Bohr model of the atom. We call these the atomic orbitals. So each line that we see corresponds to an atom losing energy. Sorry, an electron in the atom losing energy. The electron goes from an excited state to a less excited state. Now, the allowed electron energies are quantized. That means they can take on very, very specific values. So it can have an energy that is, for example, here or here, but never somewhere in the middle. Now, not only can we see these colors when the electrons lose energies, but if we supply the atom with this exact energy, we can cause the electrons to jump from, for example, n equals 3 to n equals 4. If we tune a laser just to that exact energy difference, we can control the electron and have it move from one energy level to another. So oftentimes when we go to atomic control labs, we get a whole rainbow of lasers in there that are meant to control different energy levels of the atom. You can see in this lab, they have pink lasers, cyan lasers, they have infrared lasers, radio frequency supplies as well. So all of these are used to control the electron energy inside the atom. Now, this concept is also behind today's most accurate clocks. These lines are incredibly well defined, and these wavelengths correspond to very, very, very distinct frequencies. So if we understand this frequency very well, it essentially becomes an incredibly accurate pendulum from which we can build a clock. So we can use it for that, but we can also use it to build quantum technologies like quantum computers as well. In order to do that, though, we can't just heat a vapor of gas. Once again, we really need to trap individual atoms. Okay, and thankfully we can do that. So this picture right here, what we're looking at right now are 8 individual atoms of an element called ytterbium. So it's kind of hiding near the bottom of the periodic table. No one pays attention to it most of the time, but it turns out to be really well suited to these kind of quantum computing and quantum simulation experiments. We can encode one bit of information in whether the electron is in the ground state or the excited state. And by trapping them in a line like this, shining lasers on each individual atom, we can build quantum computers one bit, one atom at a time. So let's see how we can do that. How can we actually isolate a single atom? Okay, well, we're going to do that using electrically charged ions. The same way that when you rub a balloon on your head, you generate static charge, we're going to essentially rub a balloon on the head of the atoms. By that, I mean blast them with a really intense laser, but the same essential idea is going to happen. It's going to cause them to shed electrons and become positively charged. And now when they're positively charged, if we have 2 positive charges and try to bring them together, they're going to repel each other. So if we're able to trap one atom in a line, in a space like this by applying electric fields from every direction, it'll stay in place. If I try to bring another one in there, it's going to repel, and they're going to form a nice little line because they don't want to get close together because they repel each other, but they're also being kept in place by the electric field. Okay, so let's see a bit more how this works. Now, if we wanted to trap ions live, that requires vacuum systems and a lot of patience. So to do it quickly, we're going to trap dust particles instead. Okay, so we're going to switch again to the demo camera. We're going to trap dust. So we have an experiment that, from my perspective, looks exactly like this bottom right picture here. When it's on and open, looks a little more like this. What essentially we're going to do, and I cannot stress this enough, do not try this at home. We're going to plug some razor blades into the wall and see what happens. So essentially what we're going to do is we're going to put the wall voltage across these razor blades, and that's going to apply an electromagnetic field between them. We have 4 razor blades, 2 like this and 2 like this, and that's going to apply the electric field we want kind of in the center here. So razor blade here, ions get trapped this way. I also have this component right here. This is called a variac. It allows me to control the strength of the voltage across the razor blades. And then we also have a laser beam that's going to scatter light from the dust particles in order to image them, in order so that we can see them. So I'm once again going to switch my tab real quick. And if it does not show up for folks, once again, please yell at me. Hopefully we're seeing inside the box relatively soon. I'm going to take the lid off the box. What you should be seeing right now is an electrical connector attached to a screw, and then what kind of looks like a gray background with some like kind of black paint on it. So that gray thing with the black paint on top, that's our razor blade. And right in the middle is where we're going to be trapping our dust. So I am going to charge up some dust using the classic method of rabbit's fur and a straw. So I use that to get some charge across the straw. And then I'm going to grab some dust using that straw. Now, so we can see it, I'm going to put a lid back on top of the box, and we see it gets dark again with a little bit of a green glow. If I tap the box, yeah, perfect. When I do that, we see that a little bit of dust flows into the chamber, and you can see the laser illuminate it when that happens. Now we don't have any field, so it's just falling straight through right now. So what happens if I turn on the alternating current field, plug the razor blades into the wall, so to speak, well, and put a little bit in there, and then a little bit more dust in. So we have a little bit of a field now. If I pop that in there, still nothing. There we go, a little more. Now we're in business. Perfect. Once I did that, I see that some of the dust got trapped in there. It managed to fall into the center of the trap and is now levitating there. Some of it's going out around the edge, might be a little bit of a breeze or something. One way we can fix that is just by cranking up the electric field even more and trapping even more dust inside the trap. Okay, so right now we actually probably have too many. In practice, what we want to do is lower that electric field so that we only have a countable number in there, something like 10 to 20. And then what we could do is use other lasers to shine on each one to control the energy states. I'm going to turn that down a bit. Yeah, that's a nice chain right there that we could actually think about. If these were atoms, we could actually think about using to encode quantum information and build quantum computers. But because it's a bit more fun, let's just do once more with having a whole bunch in there and seeing if we can get a big number of trapped dust particles. Perfect. Yeah, once again, they're all repelling each other due to their electromagnetic fields, due to the fact that they're charged objects. And yeah, what we're doing is just levitating that dust in real time there. All right, so with that, we'll shut down our dust machine, turn off the power for safety, and switch back to our demo. Oh, I think I got to go back to the screen share. There we go. Hopefully everyone's back into the screen share now. Okay, now if we want to do this with individual atoms, the experiments get more intense, let's say. So this is the quantum information with trapped ions lab. The equivalent of their razor blades can be seen in this image on the left-hand side here. Those 4 rods, they take the role of the 4 razor blades. And this lab here, this is all the lasers, all the systems we need. And to get an up-close view, we have a quick video here. Hopefully it shows up okay on your side. Could be a little bit choppy, but this is a pan across the optical table where we have all the tools we need to keep these ions stable and encode quantum information into them. So we see most of this is really just steering for the lasers that are used to control the individual atoms. We can see here at the back is the actual trap chamber where they're going to trap the individual atoms. And then at the back here, what we'll see is the detector, the camera that is used to generate that image that we saw at the start of those individual atoms and ions. And also we see that there's the laser beam steering here. That's what actually kind of changes which ion we're imaging at the time. So which atom we're pointing at with our laser. It uses actually technology very similar to what's used in theater projectors to do that very precisely. Okay, and then what you might be doing when you're working on there. So here they've set up their chamber. They're hoping to find an ion. Right now the screen shows nothing, but boop, there we go. They have trapped one single ion. That glow there corresponds to one single ion trapped very stably inside their trap. Okay, now if we wait for a bit longer, you would have seen more and more and more ions start to build up. We go from 1 to 2 to 3 to 4 and so on and so forth. They've trapped up to about 20 in this particular trap. Other groups have trapped closer to 100 in their traps. And once again, I cannot emphasize enough, these are really individual atoms. Okay. Now you can do cool stuff with this too. So this is a group out of Harvard and MIT, and they trap individual atoms and then move them around using lasers, a process called optical tweezers. And yes, they use them for quantum computing, but apparently they had a little extra time one week and built a little cartoon of Mario jumping on a Goomba made up using individual rubidium atoms. So this is a cartoon made up one atom at a time. This is kind of the level of control we have over these ions and atoms. Okay, so we've been talking so far, so for the last little bit, we've been talking so far about photons, about individual units of light. We've been talking about atoms, a little bit about electrons. So you might be forgiven for thinking that when we talk about quantum, we're talking just about incredibly small things. So is quantum just about small things? Well, generally speaking, it shows up with things that are on that kind of atomic level scale or deal with how, for example, light and atoms talk to each other. But that's not necessarily always the case. So if we go to the Nobel Prize in Physics that was awarded just a few weeks back to John Clark, Michel Devoret, and John Martinez, it was for the discovery of macroscopic quantum tunneling and energy quantization in an electrical circuit. So the key word here, aside from quantum, of course, is macroscopic. By that, we mean large scale. Now, we're still talking on a fairly small scale, on the scale of about a millionth of a meter, but that's about 100,000 to a million times bigger than we normally think about where quantum effects occur. So we're talking about very, very large compared to the scale of, say, an atom. Might be small compared to the human scale, but very, very large compared to the atomic scale. So it's not necessary to be atomic scale small, but you do have to get really, really cold if you're going to do that. So for our last qubit that we're going to talk about, we're going to talk a little bit about superconducting qubits. Okay. So quick refresher on resistance. When we talk about how electricity is conducted in materials, we often group materials into two categories. Insulators like rubber that do not let electricity pass through, and conductors like copper that let electricity pass through very easily. Now, these materials may seem very different, but at the end of the day, what they have is an electrical conductivity. If I apply enough voltage to the glove, a current can flow through it. It'll likely burn the glove, but in principle, it does allow some electricity to flow through. And copper, even though it's a very good conductor, will block some electricity. It does heat up when you apply a high voltage to it and try to pass a very large current through it. It will heat up because it has some electrical resistance. So what happens to conductors when they get really cold? And for this, I'm going to switch once again back over to the lab bench camera. And wrong camera, I think. There we go. We're in the right spot now. All right, so I'm going to move my spectral bulbs out of the way for a moment. Their job is done. And we're going to take a peek at this container right here. So this container is filled with liquid nitrogen. Liquid nitrogen is nitrogen boils, at negative 196 degrees Celsius. So that's about 100 degrees or so above absolute zero, give or take. Suffice to say, very, very cold. If we think about what the coldest day we might experience in Canada outside is, maybe negative 20 in some regions, negative 40 to negative 50 in some extreme regions. But generally speaking, not generally speaking, definitely speaking, we're getting nowhere near a negative 196. So some strange things can start happening when we start getting to temperatures this cold. Okay. So for example, let's see what happens to a balloon when we get to temperatures this cold. Now you may have heard, or you may have seen, that when you get into the winter temperatures, things like, for example, the tires on your car might deflate ever so slightly. That's because essentially the air molecules that are inside your tire no longer have enough thermal energy, no longer have enough mechanical energy to kind of push against the edge of your tire, cause the tire to stay inflated. As you reduce temperature, energy inside the air molecules decreases, pressure decreases. So what happens if we cool down not to negative 40, but to negative 196? So I got my bucket of liquid nitrogen here. Let's pop our balloon in there and see what happens. And we see that as I do that, the balloon starts off too large to fit in there. But as I keep applying some pressure and pushing it into the liquid nitrogen, it starts deflating. And I keep pushing it and pushing it and pushing it. Make sure to grab my tongs because once again, this is negative 196. We do not want to get our hand in that. That would hurt. You see that the balloon gets pretty much completely flat at a certain point. But the air has not gone anywhere. This is still filled with air. It just has no ability to exert pressure anymore. So if I take the balloon out and it warms up, what's going to happen? Let's find out. Take the balloon out. And I see that as it warms up, it begins to inflate somewhat automatically without applying it. No new air is being pressed in there. It's not absorbing air. The air inside the balloon is expanding and causing the balloon to re-inflate. You can hear that crunch as well if I put it up near the mic. Yeah, it's a very satisfying crunch. And eventually it'll go completely reinflated once again. Unless it pops, which is possible. I think this one might have. That's okay. Okay. We'll get rid of those balloons. They have done their job for today. And now let's see what happens to things that conduct electricity instead. So I'm going to move this bulb out this way and flip it on. So you see that we have this bulb right here. Oh, lost the balloon. We see right here we have this bulb. It's pretty dim, I would say. Not too much light coming out there. And that's because we've attached it to this incredibly long spool of copper. Now, copper is a conductor, but if we put enough of it together, it can act as an effective resistor. If you put enough of a slightly resistive material in a coil, it's going to have some resistance. So what happens if I put the copper coil inside the liquid nitrogen? Well, what we might hope to happen is that it's going to reduce the resistance in the coil and change what we see about the bulb. So I'm going to pop it in here. When I do that, you might hear a boiling sound. That's because this copper coil is at room temperature. The liquid nitrogen boils at negative 196 Celsius. This is like putting a red hot poker into a cup of water. It's going to cause it to boil vigorously. I'll put my earphone a little close to it so you can maybe hear it. And as we do that, keep an eye on the light as well. We see that as the copper is cooling down, the light is getting brighter and brighter and brighter and brighter. It's still cooling down. It's still getting a little bit brighter. Most of the effect has already occurred, though, at this point. Yeah, essentially, when we cool down objects, we see that essentially, one way to think about it is what is resistance? It's the electrons trying to flow through the material and being perturbed by the motion of the atoms inside the material. There's too much activity. It causes the electrons to react to things and slow down. If we cool things down, everything gets a little bit cooler inside the material. The electrons can flow through more easily. Okay, we can see as we take that out, that is now incredibly cold, and that light will stay nice and bright for quite a while. Okay, so a natural question to ask is what happens if we take temperature not just to very cold temperatures, but further and closer to absolute zero? There were two schools of thought on what could happen. One was that as we keep cooling things down, the electrons and everything in the material is just going to freeze in place. And the other thought was that as you cool things down, eventually what's going to happen is the resistance is going to go down and down and down until eventually it hits zero because there's nothing to impede the flow of the electrons. Now, what no one quite expected is that for certain materials, when you cool them down, eventually they hit a point called superconductivity. And that's where the electrons suddenly go from having resistance going down, drops all the way to zero resistance. And I don't mean very low resistance. I don't mean close to zero. I mean mathematically zero. Okay, and effectively what's happening here is the electrons stop behaving like they're fighting each other. They stop behaving in that way, but they actually start forming bonds between themselves. We call these Cooper pairs. Essentially, the lattice gets so chill, the protons that surround them get so low energy that the electrons traveling through them can drag the protons closer to them. And when they drag those protons closer to them, they can actually start attracting other electrons. And now those electrons are going to behave as one, what we call macroscopic quantum state. Now, one way to think about this is the difference between a flashlight and a laser beam is the same as the difference between a current in a good conductor like copper and a current in a superconductor. So, we can think about it as if we're building electron laser beams, for example. Now, what effects can we see with these kind of systems? Well, we can see how they respond to magnetic fields. So classically, so we're not dealing with superconductors quite yet, but I do have three rods in front of me. One is made of rubber, one is made of aluminum, and one is made of copper. And I have three very, very, very strong ring magnets on each. Okay, so let's start with the rubber and the copper. If I drop the plastic rings down them, they just fall naturally. But if I drop the magnetic rings, I see that the one for the rubber falls very fast. The one for the copper falls slow. I'll do that one more time because it might be hard to see on the camera. I'm going to drop them again in 3, 2, 1. This one falls immediately. This one takes a while to fall all the way to the base. Now, what's going on there is the copper is a conductor. The rubber is an insulator. As the magnet falls down the copper, it induces an electric field inside the copper. The electrons try to resist that changing magnetic field by forming what they call eddy currents, little tiny electromagnets that resist the fall of that magnet. In the rubber, that can't happen. The electrons are too bound to move. They do not resist the falling magnet. In the aluminum, it's kind of somewhere in the middle. It falls slower than the rubber, but a little faster than the copper because it's a good conductor, but not a fantastic conductor. Now, what about if we had a superconductor? So a superconductor can conduct electricity as if there was no resistance whatsoever. So if it tries to form some kind of electromagnet to resist a changing electromagnetic field, it can actually lock in that electromagnetic field. It can lock in that persistent current and use that to repel out any magnetic fields, very closely related to an effect called the Meissner effect. Now let's see if we can do that. So we do have some superconductors on us. This is a special superconductor called YBCO. It superconducts at liquid nitrogen temperatures. So most materials like mercury, for example, superconduct at 4 Kelvin, lead around 9 Kelvin, aluminum around 1 Kelvin. Materials like gold and copper, we don't know if they superconduct at all. So let's see what happens to this puck of YBCO that superconducts at liquid nitrogen temperatures when we pull it out. So this is a room temperature puck of it right here, and a very, very strong magnet. And when I bring the room temperature puck to the very strong magnet, we see that it's not magnetic. I do that, it falls off like falls off like a normal puck, like we would expect. But if I bring a super cooled puck to the very strong magnet. So this is my liquid nitrogen cooled puck of YBCO here. I'm going to put it on top of the magnet. And I see that not only does it not fall off, it's actually levitating above the magnet. If I put a piece of paper in between there, we can see that there's a little bit of a gap there. It's locked into place. It's formed an electromagnet inside the superconductor and has locked into place above that magnet. Now, if I put it on the circular magnet instead, it's not only going to be happy to stay there, it's also going to be happy to spin, even if I turn it upside down like that. Okay, so this is an effect that we see with superconductors that we do not see with just good regular conductors. I can also put it on a train track like this. If I pop it on top there, the magnetic field doesn't change around the circle, so it doesn't want to move off of the circle, but we'll be very happy to spin around and around that track as long as it stays cold. Okay, so this is an example, once again, of how superconductors behave very, very differently than even just good conductors. They behave in a way that is very, very specific to superconductors. We sometimes call this a phase transition because it is a very, very different set of behaviors that occurs once it reaches a very specific temperature. When this does warm up, you'll see that it will just stop levitating. It's a little more gradual because, of course, the whole puck has to warm up. But if we had one unit that was all kept at the same temperature, as soon as it hits the superconducting temperature, it will just fall down. All right, we'll do a quick switch back for the last couple slides. We ended up just talking about this part, so I'll skip past that real quick. Okay, so how can we use these to build quantum technologies? We can think about building circuits out of superconductors. So we use aluminum on top of silicon with niobium elements. We cool that down, not to liquid nitrogen temperatures, but actually to temperatures below that of liquid helium. So down to about 10 millikelvin. That's 0.01 degrees above absolute zero. That's about 300 times colder than the depths of outer space. That aluminum becomes superconducting. It starts having those quantum effects. We can trap it in loops and see effects similar to what we see with lasers, similar to what we see with atoms. We sometimes call these artificial atoms because they behave like atoms, but are man-made in nanofabrication centers. We put these in these devices on the end, these chandeliers. We call them dilution refrigerators. That's what lets us get as cold as 0.01 degrees above absolute zero. This is an example of the lab here. We have two fridges, one open here. That's where they're building new experiments, putting chips like this one we see on the far left inside the very bottom of it, where it'll be cooled down to negative 273 degrees Celsius. They're going to connect that using microwave transmission lines. This one here is closed up. They're running experiments at the moment. And in the back, that's where they have everything that catches the liquid helium as it boils off, recompresses it into a liquid, so that they can continue to reuse it and keep these systems super, super cool. So what do we need? So if we want to build some of these technologies, we need a lot of people. There are certain estimates out there that say something about the quantum workforce needing hundreds of thousands of people in it. And some of that will be people who are, studying at the PhD level, really understanding how these systems work, really understanding how we can build new technologies out of it. Understanding things like complexity theory of quantum algorithms, building new kinds of quantum algorithms, pushing the frontier. But there's also going to be a large, large need for people who are interested in building these systems and making them more robust, building these systems and solving some of the research and development problems. A lot of these problems are getting out of the university and going into industry where people are needed who are interested in building specific parts of these systems. So for atoms and ions, we might think about better vacuum systems. We might think about better lasers. We might think about stable and precise optical components, high control voltage, precision machined electrodes, faster readout and control. For photons, we might think about how we integrate these into silicon photon devices, high power lasers, better photon sources, better detectors, better ways for light and matter to talk to each other, better phase control and optical wavefront control of the lasers, fiber optics, satellite links, ultra-fast electronics. For superconductors, we're talking about cryogenics, nanofabrication, microwave engineering, packaging these systems, wiring them up, circuit optimization, helium extraction, fast readout and control, and generally lots of software engineering to make sure that, similar to the way we use computers today, I use my computer, I don't know what the bits are doing. I don't know anything about semiconductor fabrication or how to build transistors, that kind of thing. Not many of us do because there's enough layers of software and hardware compilation between us and the bits that we can do what we need to do without understanding all of the details. So we need things like that to eventually make quantum computers useful, not just for experts, but for really the world. Cryptographic protocols make sure information stays secure. So there's a lot of ways to get involved, some of them through physics, engineering, chemistry, mathematics, computer science, business. And if you're interested in it, there's a lot of ways to find ways to get involved in kind of the broader quantum ecosystem. So once again, that's kind of quantum information science. We're looking at how we encode information in systems that obey the rules of quantum mechanics. It's a big tent. We hope that you have some interest in learning about more different parts of it. As a quick plug, we do run a 2-week summer school open to students across Canada called the Quantum School for Young Students. It'll be this summer, August 4 to 13th. For anyone who happens to be joining within driving distance of Waterloo, you're welcome to join us for a 1-day lab day as well. Applications are open now until early May. And it's free, no cost for the virtual or the in-person component. And with that, I'd like to say thank you so much for joining us. Thank you so much again to Svetlana and the team for organizing this series. And yeah, happy to answer any questions that anyone might have.